So good morning, everyone, for today's distinguished webinar series in AI and cybersecurity. Our today's speaker is Dr. Alaa Selim. Dr. Selim is a Postdoctoral Research Associate at Dartmouth College, Thayer School of Engineering, where his research focuses on grid intelligence for resilient smart grid operations. He received his Ph.D. from University of Connecticut. Before joining University of Connecticut, he worked as a control engineer at Schneider Electric, and during his Ph.D., he also served as a research intern at Hitachi America R&D in the National Lab of Rockies in Golden, Colorado, where he contributed to applied research at the intersections of power systems, automation, and security. Dr. Selim is a recipient of Sikrosky Fellowship, the Future Climate Venture Fellowship, and the Eversource Energy Fellowship. His work has also been recognized with Best Research Award at the IEEE PES Grid Edge 2025 and Best Poster Award at Inform's annual meeting. And it also features a Best session at the IEEE PES General Meeting. Dr. Selim, the floor is yours. Thank you for being here with us this morning.
Yeah, thank you so much, Professor Prakash, for hosting me. I'm just going to share my screen. Sorry, I think I shared the wrong one.
I thought it's coming and then it went.
Okay, can you see it now?
Hold on, it's coming. I'll give you one. It has to wait. I think we can see it. Yeah.
Perfect. Okay, cool. Yeah, thank you so much. I'm going to start today with a talk title of Next Generation of Grid Security Platform for the Active Distribution Networks. So, as you know, what happened in December 2025, or maybe who didn't see it, there was a big Polish grid attack, a power grid attack over some distributed energy sources between the operators and between the site devices. This attack has able the attacker was able to compromise all the remote terminal units, control PLCs or programmable logic controllers in the middle between the distributed energy sources and the operator. So basically, the operator was blind on what's going on in the field for a couple of hours. The good thing that the Polish power grid, they have good IT security, and they were able to would say compromise with this without having to go to a cascaded failure or a cascaded outage. So I would like to say, if as a power system, from the power system perspective, if there is an attack over renewable energy or distributed energy resources or smart meters, what's going to be the impact of this attack? Basically, you'll have a voltage profile, something like that, and you can have a cyber attack or storm event or anything, and then you're going to lower the voltage curve to go to unsafe region. And then the utility will use a corrective control like Q support or tap rise or any kind of conventional utility devices to restore the voltage back to the system. So I would say it's not only about the attacks, but it also can be in the storms. In New England here, we have a lot of thunderstorms and a lot of winter storms, which can also cause the same impact. So basically, you see the voltage profile has been changing from upstream to downstream for some of the houses, some of the counties, some of the districts, and you can find them having an issue with irregular voltage profiles. So grid disruptions can arise from either cyber attacks or extreme events, and it introduces us something called hidden system vulnerability. It's something hidden, like can show up anytime, and it just need a trigger to appear and cause large service disruptions. Speaking about the grid modernization, as you know, like there is a lot of things happening for the smart grids, a lot of smart meters, a lot of deployments for smart controllers, and this is all over the nation. And this is great, but it's also at the same time expose, or I would say increase attack surface for the attacks. And this can result in a lot of cyber security incidents probable to happen. Utility sector is known, according to Reuters last year or before last year, according to there's 70% increase of the attacks and specific to the utility, more than any other sector, more than the water, more than the health, or any other, I would say, important sectors. So that make a problem that, yeah, we have noticed incidents of attacks, and we need to find a way how we can secure or build the next generation of the cybersecurity platform for power grids, and specifically for the distribution network. For that figure, you can see a couple of instances have been already happening globally. So it's not only limited to the US, but also many other countries has been witnessing a lot of attacks. Maybe if I can pick up example, let's say in Ukrainian grid, maybe some people are more in the security research. You know that this was a big issue that happened in 2016. That the attackers appeared to be a trial run of a much larger attack, and the crash override malware communicated directly to the ICS to turn the power off. So they were able to compromise the grid devices, and were able to cause a big power off and cause blackout as a result. Yeah, and there is also a lot of incidents which can exactly the same way. And as I said, there is a lot of interest to attack this power grid or service. That's created a big problem for the researchers or engineers to find a way how to protect it and how to defend it. So now I'm going to move to our research framework. So basically, just to identify what's the attack vector or how it's being constructed. It's something that's function of the space and time, and it can be triggered for any assets and cause a change in the measurements. So basically, if you have a smart meter, a real-time measurement, and then you inject this L function, which can be triggered by the attacker, basically the YK will be added some value and will be changed to another value in terms of like the magnitude and direction, and also it will be kind of like stealthy, so that it can be able, when you simulate the power flow again over your network, there is violations that is obvious to happen in certain nodes. And this we can see the attack vector was success to cause disruption for the service. So the main question here, how can the attacker construct a smart or a kind of, I would say, intuitive spatial temporal trigger of measurements, and then can cause as well a voltage violations to the system. So this L function is kind of tricky to design in terms of the space and time, and also can be oscillating. It can be back and forth. It can be just single trigger. However, the thing here, how we can design it and how we can make sure it causes impact of violations. According to the literature, there is many attack types has been identified, like false data injection, denial of service, timing attacks, load redistribution. For the attack surfaces, as we said, like there is many, and they are like very increasing as much as we go to the grid modernization direction. We're gonna have more control centers, more automated systems, more smart meters, and more smart inverter controllers. And also, we're going to have to compromise, or I would say to protect this attack surface, we have attack detection methods, which is started from state estimation, how we can have a state estimation method which can prove to you that this is kind of issue with the residual, which not normal or anomaly, and then you trigger your defense. You also have anomaly detection. If you find something weird with the control commons, you have machine learning, and you have now the hybrid cyber physical and how you can employ them within the system. For defense, started from access control a couple of years, and defense in depth, which involve many things you can do, controllers, controlling devices, anything you can able to control within the system to restore your voltage profile back. You can have it, and also moving target defense and resilient operation work. And lastly, at the end of the day, you need to validate this. As I said, like distribution networks is and transmission networks is kind of big networks, and you need to have either a simulator or a real-time simulator or a simulation model that can emulate the behavior of this until you can have kind of solutions, and you can go for other more verification like hardware and loop, and building your own digital twin that can perfectly emulate what's going on. So speaking about the smart grid, so smart grid, it has a couple of layers. Firstly, the cyber layer, which is composed of the communication, computation, and control logic. Physical layer, which is composed of the power network, DARs, loads, and devices. And a coupled layer between both of them, where you can have the connection between the physical layer and the cyber layer. Sometimes we use, for our simulations, we use RTDS or RT, which can be perfect to have coupling between both of the cyber and physical layer. So you can have a physical, I would say, or a feasible solution that can be making sense to the real time grid operations. One of the two examples in the literature as well, there is one of them has been proposed last year. It was a great, I would say, modeling for cyber and physical model. It was the model, the cyber layer in Mininet, and you make the communication graphs and everything, and how we can emulate the attacks over Mininet. They use also SDN controllers, which is also now dominating in the power grid to be as a centralized controller for the switches that involve the measurements and all the data you collect from the physical side. And on the right side, we have this model as well, has been developed by NYPA, the New York Power Authority in New York. So they have also developed this is kind of the communication network, the physical, the cyber layer, and this is its physical layer. And this is how they emulate the attacks and how they can have a SCADA system, which can give you the full coupling between the cyber and physical layer in this module. Challenges in the distribution networks. There is also actually a lot of challenges. So I would say it's very high dimensional system. You have a lot of points to control. You have a lot of observations, and you have a lot of devices to take care of it and control with respect to uncertainties and history and forecast. You have also a lot of uncertain profiles. You never know like what's going to happen next tomorrow, like today or next week, for the solar profile, for the load profile, for many other measurements, even for the voltage profile. So it's a lot of uncertain operations. And on top of that, you have non-convexity. So basically, active distribution network, it's a system which is unbalanced, three-phase unbalanced, and it has non-convex, I would say, formulation for the constraints to get the right power flow. It's not easy to solve by by direct solver. And these challenges give us to the second question. So how we can find, based on all of this, the vulnerability of the active distribution networks, and we can ensure that we can solve the power flow in the right exact way and have the resilient safe operation being applied. This is kind of the proposed framework for this research. So we have the controller we built, and we link it with a grid simulator and closed loop with our states, our observations, and iterating over this for every time we're gonna simulate or we're gonna train our controller. For the methods we use, there are many methods. We can start from historically, like maybe a couple of years, there was heuristic methods and Bayesian, and now there's also model predictive control, and now we have DRL, safe DRL, and hybrid, where you can have physics informed machine learning. So you can train your system, and you also link it with some physics of what's going on in the system. So you make sure that the control action every time you execute is going to be very safe enough, and I wouldn't say it's guaranteed to not cause any violations or any abnormal behavior. Again, the problem of power grid is very sensitive, so that's why the safety part is very considered during the evolution of the controllers we build here. For the grid simulator, we have a couple of like things open source and commercial. We have OpenDSS and GridLabD for sure, and SIM and Synergy Electric can be used from the commercial side since they are already used by a couple of utility companies we have been working with in US. I'll go maybe more specific about the DRL, since maybe most of the research I've been doing here are using the deep reinforcement learning. So basically, deep reinforcement learning, we identify a Markov decision process. Basically, we identify a couple of states with respect to time horizon. And every state, if you do kind of control, let's say to the grid and the battery, you will come to a next state in the second time step. This state can be good or can be bad. It depends on the actions you have been doing. So, for example, if you do an action which is not studied well or not planned well, you can come up to a lower reward, which means lower cost function, which means that the system is doing not performing in the optimal way. On the other side, you can have these two actions improve your system and keep you at least within the best reward you can have if you have the right control. So it can be summarized that you have a state, you have an action. So now you have an issue with the voltage. At the state, you can make an action, which is, for example, increasing the power dispatchability from the smart inverters. And then you can assess your reward, and then you update the policy of your controller. And then once you come to the right policy, or I would say the most policy you are confident with, you can have this controller to be deployed in field, and raise back the voltage when it comes to any issues, either from attacks or extreme other events. So attack surfaces. So in this talk, we're going to talk more about a couple of attack surfaces. Firstly, the attack surface one, which is the load altering settings. So basically, if you have a smart meter and you were able to use a false data injection attack or man in the middle and compromise or change the values inside the smart meter, which is maybe connected to ADMS system and connected to the DERMS over the net, like the grid operation side, you can observe a couple of changes in the load values. So the original value, for example, 40K become 80K, some original become 20, become 10. So you're increasing the voltage in one of the settings and in one of the phases and decreasing in the other phases in a very stealthy way. So you construct this kind of attack vector, and you come up to kind of like objective as an attacker, which you want to increase the violations and the unbalance as much as it can be. However, with respect to the attack budget you don't have a lot of freedom to inject more or absorb more power, because basically you'll be easily detected, and it will be a lot of effort as well for the smart for the attacker to compromise many devices. So you need to assess both of them in the right way, so you can construct the stealthy attack vector. So if you come to distribution networks, so you can see that you have like you have the part of the system can be compromised by the attacker. So in our experiments here, we did like less than 10% of the nodes has been compromised, which is kind of one of the theories that if you have compromised less than 10%, most probably it's going to be hard to cause violations for the system. So if you have around 10%, that's fair enough. If more than that, it will be very a lot of effort for the attacker to compromise all this kind of devices. The defender will be in this work we use non-cooperative Stackelberg game. Stackelberg game was really powerful in terms of you have attacker and defender. None of them know the strategy of each other, and you want to have the best strategy of the attack so that you can propose a lot of vulnerability to the system to be studied later. And the defender want to know how he can deal with this kind of vulnerabilities in the future. So it's a game between the attacker and defender in a non-cooperative way. None of them, they know each other. None of them know that this one is attacking specific assets or protecting specific assets. But at the end of the day, we need to find solutions in the both sides from their perspectives. And I would say model protective control and AI models was kind of not implemented here since you don't the policy is hard to quantify it, or how to find its trajectory. And the same for AI models. It's going to be a lot of training for this data. So that's why we come to that work with the Bayesian optimization to convert to get the right optimal attacker strategy and the right defender attack strategy, like right defender strategy. We come to the third question here. So can we simulate a Stackelberg game between attacker and defender to get their best strategies given no one know each other? The answer is yes. Basically, if you put objective for every one of them, and then you simulate the both strategies and see how they can converge. Bayesian optimization was doing a great job here in terms of conversions, in terms of giving us the load multiple identifiers. This is the attack vector that has been offered by the Bayesian optimization. And then we quantify in terms of other state of art. So I use here two black box models, which is also very fast to give you the load identifiers. We had a good results in terms of violations after the attack. So we were able to get a lot of violations after attack, which proved that we have a good attacker strategy. And we also got to have less violations after the defense, which proved that we have a good defense strategy compared to the others. And this is all subject to the minimal attack budget. So attack budget, I mean, as I said, like it's kind of the power you're gonna inject or absorb from the smart meter when you compromise. As much as it can be lower, that would be great to make sure that the system is very stealthy. Yeah, and this was yeah, maybe I just forget to mention here. So this was has been done in a snapshot solution. So we doing the like all the Stackelberg game in kind of snapshot. So every attack and defender he keeps solving the power flow in one snap, reporting back to the other, and doing this repeatedly. So this work also can be extended to load time series, and that's what we have been doing here as well. So you can see that the load multipliers for every phase. So this is phases S1A, it's a node, number node, and this is how, again, as a time step, how the load multiplier will look like. And as I said, it has been designed in a spatial temporal way, so or a spatial temporal way. So you have the right location to increase your attack multipliers, and you have the right time to also do that. And this can result in firstly you have less violation and suddenly come up to a higher violations than expected, and it never it's also be also hard to come back to normal operation unless you have a really good protection mechanism. This is how it looks like. So basically, after the attack, you see the voltage almost collapsed. The defense, we will raise the voltage profile. However, in that framework, we lose some of the nodes when you did the load shading so that we can redistribute the load flow or the power flow. And we get most of the nodes, which has a big issue with the voltage profile, to come back to the security limits. Yeah, so the violation and then load multipliers reveal a time varying attack severity, and it's something which is very important to consider for in terms of the time or in terms of the nodes you are compromising. For mitigation, we proposed here, we try to do this in the lab. So basically simulating the physical layer on this side and simulating the cyber layer on that side. So you have the RTAC as a controller. I used here all the algorithms we use, either Bayesian or DRL or any other things we do it in a workstation, and then we send the final control comments to the RTAC. RTAC act here as kind of, or the real-time automation controller. It acts as kind of data concentrator. So it's basically just sending back and forth the data. The reason for that, the RTAC doesn't have PyTorch and some libraries that we needed to be trained on, and also doesn't have some of the controllers or things we can do. However, the Modbus communication can be very straightforward, very fast, and can just use RTACs. The idea that RTAC is going to be our main focal point inside any substation. So if you want to propose any solution, this can be the first gate to come from to deploy your solution. And then you send it to the SDNs, which is managing a couple of switching routers, and back to the JetNet in the RTDS. One of the proposed solutions is that like you open a switch. So in this problem, we used topology control. You can open and close some switches. And you can see that the sec line, and this is a screenshot from the RTDS. So the sec line, it's something great because basically if you have a sec line within staying until the end, means that you have all of your nodes within the limits. However, some of the nodes will be shaded already, as I mentioned, as a solution that you had to do. But the good thing that the SEC line will remain within the voltage limits and not converge or diverge to other voltage levels within the simulation time. The second attack surface we have here is a smart inverter set points. So basically, you attack in the previous attack surface, you attack the load or the smart meter. Now we attack both of them, and we focus more on the DER by constructing also specific attack vector, and then trying to cause violations for the system. Here, we didn't focus in building the attack vector as much as we can defend now. Like this work has been done to basically say now we have an attack vector has been constructed and has proved to be a violation issues. So how we gonna mitigate the impacts of this attack vector, given that it's already having big issues with the system. So you can basically, you have some percentage to tune, and you can see that the voltage profile, when you make -10 or minus, you reduce the generation of the DERs. It comes to 92%, which is a lower limit. And also the same case, if the load you change it, increase the load kind of random way. And as I said, we use normally a specific part of the system, yeah, not all the system, or maybe a big part of the system, but a very small part of the system within 10% of the network. And then you can see that yeah, the voltage it has been issues, and also the power losses was another metric could be considered. So it become increasing as much as you play with these two operational profiles within the simulations. The mitigation strategy here, as I said, we were focusing more on this. So basically, you have now the attacks on the two attack surfaces, as meters and inverters. It has been propagated back to the distribution network. We co-simulate it, and then we use our DRL or our soft actor critic method, which will be kind of say, like trying to control set points. We have around, I think, 100 set points in the action space. So you have a lot of points to control. You have a lot of devices to control, and a lot of smart inverters as well to control, which is not compromised, which is very important. Yeah, since some of the things which are already compromised, it will be hard to control them within this framework. Um, the expectation is that the voltage should be dropped, the loss of critical load, system losses, number of voltage violation. We try to do the other side. We want to minimize the voltage violation, restore the loads as much as we can, minimize the system losses, and reduce the number of violation. And that's why you will see normally if you counted it in a time series heat map, you'll see that for the two figures, yeah, sorry, this is maybe looks to be the attack figure, and this is a defense figure. And the only way difference between them is just the voltage limit. One of them is really below 90% of the nominal voltage, which is not sufficient even to operate your device. And the other one is within the normal limit above 95% of the voltage magnitude. So the reward function for this controller has been designed in a simple way. Like you have four things, four parameters to consider. It's a max function. That's why you see some of the things you want to minimize in negative. So power losses in negative, voltage violation in negative, power shading in negative. You want to minimize all of this, and also the deviation between the normal voltage for every node and the current voltage we have now at the time step. So you can see if we compare to the other state-of-art methods, you will see that for the first figure, there's a big, I would say, deviation in some of the nodes that are already having big issues. And even though you use rule-based controllers like volt var, volt watt, or even non like or MBC, you still have some issues with your voltage profile. And then you come to the same case. This is, for example, increasing loads. This is increasing DRs or reducing DRs. So you have either over voltage case or under voltage case, or you have a big combined case. Like you assume that the attacker was be able to to have an effort to do a compromise for both the smart inverter and the loads, and was able to get the profile back lower to the system. So in these three cases, it shows that the DRL controller or any proposed controller which has been well trained on the system can definitely give you a good strategy to maintain your voltage profile within the system with respect to any changes in the attacks to the smart meter or the smart inverter. Yeah, the third attack surface, or maybe the one before the end, before the final attack surface. So this is a volt var setting. So now we have volt var setting in many smart inverters, and basically it's a volt var curve. So you have a dead band region, and you have some region. If you are below a certain region, you need to inject more reactive power. If you are above a certain voltage limit, you need to absorb some reactive power. So this function, this piecewise linear function is very important to determine like how you're gonna inject power and how you're gonna absorb power. And the attacker can change the settings, can change with the settings to make sure that all of them have a feasible region to be within. However, the attacker will be try to still remain within the feasible region. However, try to cause a lot of issues. If you solve it over the power flow, like over OpenDSS and through over the network, you'll see a lot of issues with the voltage levels and the power losses over the system. So VoltVar settings is very vulnerable to attack, and that's why we started to do some simulations of generating mini control rounds. 14 of them was flagged as suspicious because basically some of these control comments in the bottom can cause a lot of violation issues, up to 1,000 violation. We used here a real feeder around 5,625 nodes, and was in this one, if you find that one of the round of attack I do for volt var, I can reach up to 1,000 violation or maybe 500 violation within this range, which is a big flag. Like basically, that means you have around more than 20% or 10% of your system has issue with their voltage levels. However, if you have a voltage violation up to 100 within system, which when we studied the system in normal operation, it has some violation for sure because we have a lot of DERs, a lot of storage, a lot of injecting power sources. That's why we can expect to have violations for the system. However, the maximum range we can see that it's around 100 violation, not more than this. So basically, if you have a control command which can cause the system to go to more than 100, this can be suspicious control command, and we can maybe reject it as as an attack, as a defender, or as a detector mechanism. So we started to do that, and then we started to see which like point in the Volvar curve more vulnerable than the other. So we see that V4, VF, VR, and V5 from the curve is much more vulnerable to attack, and the others is kind of maybe more similar. And also we tried to do something else. Like we tried to see if you have a detector, conventional detector you put in the detection layer, what will happen if it's uncertain actually about its decision. So the problem here, if you have uncertainty, that means the classifier or the attacker, that the classifier can wrongly classify the attack and maybe assume it's at normal and it's attack. So now we try to play with this to generate uncertain samples. Give me the samples that you as a conventional detector are uncertain of. We have a data set and then we inject it back to the full data set so that we have more, I would say, data augmentation and more data that we having also original and uncertain samples. So we ended up with a big tabular data, I would say a large data set in tabular format since I solved this problem in Snapshot. So yeah, we focused mainly on a specific time of the day, which is very vulnerable. And then we generated a bunch of data, including original, uncertain, and also adversarial samples. And we propose this framework to detect the mechanism of these attacks. We started here with a data set prepared and then using quantile transformer to process it, and then having ResNet with a couple of blocks, which is really great in terms of you have a couple of values for every classification accuracy, and then you make in sample average for all of them. And on top of that, you also tune the hyperparameters for ResNet. It's very important. So we were using Optina, which was kind of great to improve the performance of the ResNet. And also we have the loss function being trained for the whole ResNet blocks altogether. And we would come to a very, I would say, good like accuracy and precision compared to the other state of arts, including transformer and TAPNet, which is powerful as well in dealing with the tabular data. The intuition to use ResNet was basically we reviewed we saw a paper from the CS domain that how we can leverage the deep learning models to deal more with the tabular data, and I would say ResNet and other maybe forms or other variants of this prove to be a good way to deal with this data sets. Maybe the adversarial data sets, the adversarial attacks as well, we have considered in this work. So basically, imagine you have a stop sign and then you put a noise. So you have, let's say, your own, I would say, classifier, and it visually classify that this is a stop sign, and then you put a signal on top of it, and you have this classifier giving you that it's a yield sign instead of stop sign. So basically, you make a perturbation over the pixels of the image, which make you classify wrong. This is also very likely to happen in power systems. So if I have some data and I put some noise over them, my classifier or the ResNet or any other way can give the wrong answer. And that's why we try to study this well, how we can have a lot of, let's say, a couple of methods like fast gradient, black box, and white box models, which work in the two ways. Like you want to increase the misclassification as much as they can to be having the most strongest adversarial sample, and at the same time with a minimal perturbation you can do. So you don't have a big perturbation, which is can be obviously detected. That was basically the trade-off to generate adversarial samples and reinforcing back your data set that you originated before. Hop skip jump was doing great in CNW, and I would say the misclassification was not that high, but the perturbation was very small. And same also for nearest order optimization, which sounds to be a good thing to have. And that's why we were coming with this framework to adopt to generate the adversarial sample. So this is how the hopscape jump looks like. Basically, you have a benign Volt-Var curve. So you're gonna give Volt-Var curve coordinates, and then we're gonna make a Monte Carlo probes, and then you have a direction estimate over the function before the function. The most thing you need to know here that you come up to a decision that the function is not equal to the function you classified before, which means that you're now able to misclassify. So if you're able to reach to that point, to this rhombus, now we can say you have reached to the right adversarial sample, and you have your search space you keep updating and clipping within this criteria, within this epsilon, until you come up to always to the rhombus. And if you didn't come up, you will be coming back and forth until you find the right noise, which can cause you to this stage. The problem with this work is very computationally burdened. Like it's taking a lot of time. Dealers order, for example, optimization was taking a couple of hours, can be extended to a couple of days as well, and that was expected, because it's very hard to find the noise which can do this kind of higher misclassification for your already proposed algorithm. And this is how it looks like. The perturbation, as I said, like you can see V4 and V5 was having the highest perturbation. Since according to the shape form we showed before, this are the most two vulnerable points to cause a lot of issue. That's why the perturbation was mainly centered on these two points to cause a lot of system violation issues. So this is how the perturbation is being divided, and all of them within 0.2 per unit with the coordinates of the system. So how to mitigate? One of the things we were proposing for the mitigation of the Volt-Var attacks is building a detection security layer, which is based on large language models. Large language models is fine to be having more intuition. So now tabular data is great to deal with, but if you have more text and the more kind of other models, or I would say multi-models to be informed with, that will help you in this detection mechanism. So if you have a data and then you convert it back to text, and then you have a detector, so the detector will be basically classifying this text data, not the numerical one, and we'll convert it back to numerical and send it back to the system if it's fine. If it's wrong, so he will send it back to the attack to the scatter operator, and the scatter operator will keep iterating over this to see how we can mitigate it. You can see that the comment can be chef x1 by 0.07, chef x2 by zero point 0.1 units, and chef x3. It's like kind of control comments you're mentioning, and you train this large language model over this one. In this work, actually, we used a distal PERT. It's kind of, I would say, small technique, but it was very powerful in classification because you can't compare it, let's say, with GPT 4.5 or GPT 5.2 or Gemini 3 or any of these versions, because basically we don't need all of this knowledge for that. We just need a classification based on the fine-tuned models, and we want it to be not expensive also in fine tuning. And that's why we come up here with I would say a good idea that how we can get the distal BERT classifying to us the normal sample and the detection sample and the attack sample. When it comes to real-time deployment, it's always maybe, as I mentioned in literature, it's something we really care about, how we can make sure that this proposed detector or proposed defender can work on the right way. And I would say in this experiment we use a Typhoon virtual high hardware in loop as well to just get more insights about the battery size, for example the latency, inference, the computational performance, and all of that. So we come up to that we can do all of this detection from end to end. Like me, basically, I'm running the Python script in the background, and I'm sending it back to the Typhoon in a hardware loop and detecting the samples that has been ejected. It's all within milliseconds, maybe maximum of 4 to 5 milliseconds for this task. So in terms of computational, I would say real-time testing, it's kind of acceptable for this kind of platforms. Yeah, the last attack surface we have here is a software-defined network. So also you can attack now smart meters, smart inverters, both of them, or smart settings inside the smart inverter. However, also SDN can be very vulnerable to attack from the cyber perspective. And if you were able to imagine you have a couple of switches and you have a controller, SDN controller, even having TopoGuard to coordinate the topology of the cyber side, and you were able to I would say make a detour or kind of make something we call topology poisoning. So topology poisoning, basically, you did some mess up with the communication graph and connecting the routers and switches together, and then you inject your data as a way of man in the middle, and then you change some values, let's say volt var curve or power PQ set points or any other things. So the attack will be mainly on the cyber side, not the physical side, as maybe we have shown in the other work. So simulating this in our machine, we found that for using a node-RED interface, just to see how this is how the IEEE 123 bus system being simulated, you can see that there is a lot of violations happening over the system once you trigger the attack. And we have a list, like not since it's kind of more a realistic system, so you don't have a lot of observation except a couple of nodes. And you can see that the average for some of the nodes would be very high violations because you were able basically to make a topology poisoning, inject a man in the middle attack, and give some wrong PQ set points from SDN, and the SDN basically he didn't still until now realize what's going on, since the flow rate tables were all compromised, and he assumed it's the right one. And to detect that, we used cyber detector fusion. So you have to have I could say comparison between the residual between what's going on in the physical side and the cyber side. On top of that, you have a TopoGuard. TopoGuard is some machine delivered by Texas A&M for the topology poisoning. So you have it as a kind of your decision tool making tool. So if you didn't flag something or flag some any issues or a sign of things, okay, that's great. If it flags some issues, you will end it with what's going on in the cyber side, on the physical side, and then you will start to make the defense. So basically, the attack still triggered the same time as before, but you were able to dispatch more power during this whole time horizon. So you make sure now the attack is happening. We can't stop it. However, we can do the defense mechanism to do inject some power so that we can get the voltage limits within the time until you find someone who can release a compromise in the IT network so that you can get back to the normal operation. However, this one will, I would say, the more perspective that coming from the power side, so you were able to compromise it. The vision now for the security platform is maybe the title of today's talk. So basically, you can have a great large language model detectors built on the top of your smart assets, smart meters, smart inverters. You can have also deep reinforcement learning or any kind of controllers, which is can control all your DRs with from the other side, and all of them working together to enhance the security platform. This can be achieved that through cyber range vision. So cyber range vision, like it's have been developed by National Lab of Rockies or former NREL. They were having a couple of cyber layer well modeled and physical layer well modeled, and you can have this kind of thing. So it's very important to have, I would say, every like as a researcher or the engineer to have this kind of environment so that you can always keep update with what's going on for the attacks happening. And that's why, like say that it has been said that why yesterday's power grid security will not work tomorrow. So that's why you need to have your digital twin, which is always up to date. Some of the great things has been done here by Nozomi networks. They have been already deploying from the industrial side some kind of physical layer security in terms of a Guardian tool or smart polling. Sorry, it's being employed over the remote terminal points like pay control units, and also they did something good for the cyber side in terms of the switches and routers. So this has been already studied, and it's not only limited to substations, but it's also in any industrial systems it's studied. And there is also I see they're now updated with having AI-driven anomalies, so it's now coming to deployment for the industrial operations. And also we can see here the some also like Dragos have been doing great work in terms of assessing the vulnerability of every asset. I would say the thing which has been lacking is for us as a power system engineer, if we can improve this resiliency matrix for every asset based on our knowledge, based on our simulations on the active distribution networks, that definitely can have a lot of value to this kind of resiliency or resiliency simulation tool assessments. And lastly, we have here Clarity. So Clarity is been also kind of reporting system, give you all the devices been impacted. So basically, it focuses, for example, in your firmware, some kind of OT activity which is malicious, which maybe we have been showing during this talk. A couple of cyber things which is also kind of not normal, and he can tell you that which device is more vulnerable, like your BLC, your controller, your remote point, and prioritize all the top risk high assets. This is also great to consider. So you can definitely, based on our research studies, we can link this to this platform, and this kind of devices can be more, or I would say, this kind of study can be more enforced by more knowledge from the power system perspective. Lastly, the research direction. So I feel like there is a lot of hot topics here. One of the things we have been working on is using the reinforcement learning from AI feedback. So basically, reinforcement learning from AI feedback is you have some large language model which can tell you which samples be normal and malicious, and you have a reward model which you kept training it to refine your system again at the ground truth. And this model, this framework has been adopted in many CS application. That's really good to have it if you were able to fine tune it and having as a good platform for our systems. That can definitely give a lot of value to improving the large language model reasoning and also giving them more aligned with the physical informed machine learning that's been informed by the reinforcement learning. And lastly, I mean, and the second maybe or the maybe most booming now with agentic AI, how we can have this all in kind of agentic AI. So how we can make your detector, your awareness, your simulation, your planning, all of them, every one of them is in its own agentic AI agent, and linking all of them together in a way which can help you, I would say, orchestrate the framework, and having also a better runtime behavior for the system operator. Lastly, I'd like to for sure ask my like thank my collaborators, my faculty, and researchers and my advisors for that work, and for sure our lab for being working on this work, and also for our potential fund bodies. And I'm glad to take any questions. Yeah, thank you. I hope it's on time. I'm sorry, it's maybe muted.
Oh, thank you. Thank you for the great presentation and appreciate for sharing your thoughts. And now we can take questions on the chat. Folks wants to jump in and or want to ask questions. Feel free to turn on your microphone and ask question. Who's want to go to the first question?
So I have a quick question, if that's okay. Um, uh, Hi, it was a great presentation, a lot of work, uh, really good work so throughout. I just want to know like about the attack surface 2, I guess it was on the voltage violation. How exactly did you do the mitigation there? I wasn't probably I didn't wasn't clear enough about that. Yeah.
Right. So you mean for which attack surface?
Attack surface 2, I guess.
Two. Okay.
Yeah.
Perfect. Yeah. So yeah, here we go. Yeah. So attack mitigation here. Basically, we had a deep reinforcement learning controller. This has been trained over a cost simulation setup. It has been having a lot of observations from what's going on for the distribution network in IEEE 123 bus system, and then it was feedback to the defense mechanism, and then this defense was being forming its own policy. And then after that, the policy it should be in terms of the maximizing this reward function as much as you can. So you want to minimize the voltage violations, you want to minimize the power losses, and you don't want to go for load shading if possible. So and your action space basically is controlling the smart inverter set points. So you can control P and Q set points for most of the system, which is not compromised. So for example, if you have yeah, this part has been already compromised. You have one, two, three, four. So okay, so now you have access to other DRs, which you can control them, and they will help you to resolve the power flow again and get the voltage profile back to the safety limits.
So basically, you're using maybe neighboring node points to supply enough set point generation so that it can support the.
Right, not necessary. So I'll tell you, the DRL is something. It's some. I'll tell you, like it's kind of training. It keep training back and forth in
Mhm.
environment. And if it's fine, for example, we didn't see if the neighboring maybe will be the best. Maybe the other ones, because this DRs, all of them different capacity, right? So maybe someone is maybe neighboring but have a lower capacity to impact the voltage profile. But maybe someone very far and maybe have some kind of connection according to the topology configuration can impact it or can improve the voltage profile much better. So the DRL figured this out. You don't need to, as for me, for example, or as someone who solved the optimization problem, the answer of this is being developed by DRL in terms of action space. So it can tell me which action I can do for all of the DRs, every set points in like exactly for all of them. I would say again, not necessarily neighboring, maybe someone in the far, but at the end of the day, you are coming with this mix, which help you to get the voltage back.
Of course, last just one quick thought. Have you
Yeah.
considered like the spread of the attack, like how much could it spread to the neighboring node points in some
Right,
ways?
right. As I said, like yeah, in this study, we were thinking that the attacker to be within, I would say to be very smart, we consider a smart attack, or maybe the main assumption you have around 10% of the system to compromise. If more than that, it will be very like obvious. You know, this is now kind of a big attack. So basically, you'll trip many things. You will make an island. So we don't need even to consider still redispatching power and stuff. It's now become an urgent case. However, we assume that the attacker is smart, still see no one can detect it, or obvious, like obviously they have something which trip protections or maybe come to the transmission layer. However, it's you try to prevent it from spreading out. So if you do this kind of practice of injecting or redistributing the power flow, you will definitely prevent this from giving a cascaded attack scenario.
Thanks.
Fazli, you have very wonderful question. I want to applaud you for very. I had written on some questions what you asked. I appreciate it. Where are you from? Which university are you from, Fazli?
Oh, I'm from West Virginia University.
Super. Yeah. We have more questions. Sakshi, have you considered also taking into account the redistribution tax? Also, for LLAs, did you face any issues related to varying time scale as metered data was being attacked?
Okay, great. Yeah, I'm trying to get the question. Sorry, let me stop
From the
sharing.
chat. From the
Yeah,
chat.
the chat. Yeah. Awesome. Okay. Um,
Did you consider load redistribution attack?
yes. Yeah, this is a good question. We considered load altering attacks morely, so it's kind of also kind of similar. So the load, I would say, yeah, the difference maybe redistribution attacks. Yeah, it's more focus on the how we're gonna redistribute the loads. In our case, we do a load altering for different phases. If I may share my screen quickly, sorry. Yeah. So for example, if you have here the load multiplier, yeah, so basically we construct the load multiplier in a smart way so that you can have some of them overloaded, some of them underloaded. And based on this kind of configuration, you end up with a big issue with the system. So yeah, it's a broader consider. I see there is a part of the question about the LLA as well, the load altering attack, I think. Face any issue related to varying time scale. Yeah. Now, yeah, no, we didn't have face an issue. So I did this as well in a time scale. So this results has been done in snapshot and also time scale. This is the time series results. So you can see that we make a time step simulation and we keep attacking for first couple of steps, not to do a lot of issues. And then suddenly at a 5 time step, the violation increased very heavily due to the like the well-trained load identifier matrix.
Cool.
Yeah, hi. Just to interrupt you,
Yep.
I wanted to know, like, since you're taking voltage as the impact metric, right? Is that correct?
Yes.
Yeah. So I wanted to know, like, you are basically altering the load demand, or are you altering the actual load information?
Right. Yep. We are
So,
patient. We were changing the smart meter power value. Yep.
yeah. So, like, can I know what is the rate at which that data is getting streamed? Like, what exactly the measurements which you are taking up, and at what rate they are coming up? Since
Right.
you're
Yeah.
taking them as like considering them as real time. So I just wanted to know, like, what is the granularity you're considering and assuming, like.
Yeah, yeah, great question. Yeah, great question. So yeah, in real time, so this one has been done in like this work has for maybe this part of work has been done on OpenDSS co-simulation. So we have very fast time of retrieval. You can for every time step, it's kind of you assume that you have a couple of milliseconds, and then you keep retrieving for this time. However, you can do in normally in OpenDSS, what control us the time step is a profile. So, for example, in this case, I study, let's say, one time step can be 30 minutes, can be 50 minutes, and then I change the load profile and the radiance and everything within 30 minutes according to the available data. When it comes to real time behavior, it's a different story. So, you have to collect the data within millisecond every time, and you wait couple of you do some buffer because real-time execution it takes time as well within a couple of seconds, so you have some buffer for your Python code to get the values and assess, and then you execute your control action or your load altering metrics so that you can see the violation. So you can
All
see here, right?
right.
It
Yeah, all
answered your
right. I,
question.
I get you. Yeah, I would just be connecting with you later, like after this
Sure.
thing.
Yeah.
Anyway,
Yeah.
thank you so much for taking up
Yeah.
the questions. Thank
Yeah.
you for
Sure.
the
Thank you for
presentation.
your questions. Yep.
Thanks.
Okay, we have a couple more questions. What kind of impact do the SDN attacks show on the system latency and performance?
Great. So yeah, I think I see a lot of cyber people here.
Oh,
Yeah,
it's
that's
Cybersecurity Central. Like we have a lot of questions. It's good. I appreciate everybody.
yeah, that's awesome. Yeah, so myself, I'm speaking about my background. I'm more power systems, so I will tell you what happened in the SDN, maybe from what happened in like in power system and also for the cyber side. For the traffic, basically, what we do here in this SDN work. Basically, you have a couple of switches. You assume there is a regular a collection of data from flow rates. So like you sorry flow tables, and you keep having all of this information circulating, and he do the checks, and then he keep controlling all the measurements. So every router here has, or every ring has some values. Some of them have SCADA values. Some have the edge devices, like the devices of the smart maybe meters for voltage and current. And basically, you come here in the middle so that you can make a detour. So the data, when it comes to flow, like instead of sending from a ring gate, this is myself sitting here as a SCADA. So the data will not be coming to that way. It will follow another detour because the topology poisoning has been in effect. And then after that, you can manipulate with the man in the middle algorithm. You can definitely change your values. This can happen in very, like I would say, when I run the code for latency issue, it's something in the seconds or milliseconds. It's very fast. You can trigger that. The thing here, I have to tell you that I'm using Modbus. So Modbus doesn't have encryption. It's not like maybe DNB3 or not other techniques which has more encryption things to do so that you can change the values. So that's why I was able, for that strong assumption I have as a Modbus, I can able to make min in the middle and change the values over the registers and manipulate the whole system. However, if you have another communication which is very encrypted and very strong and very corruptive, I can't I can't simulate something which can assume that it can able to decrypt it and also change the values.
Okay, good. We'll end with one question because I got another meeting in a few minutes. Last question. How do you address the overfitting and underfitting when you talk about deep reinforcement learning, or detection models in the digital twin? Do you
Yeah.
have you accommodated that in your research?
Yeah, that's a great question actually. So we had this issue on overfitting. So sometimes you use a DRL, you find that it converges very fast and reach up to the reward value within 2 or 3 episodes. That means there's something. There's no challenge actually to solve. So that's in that way, you need to really make sure that you have the right Markov decision being enforced within the system. So you can't have, for example, you need to make sure that you have the right states, the right actions, the full hierarchy of the Markov decision. DRL cannot work in any framework which has for example, no Markov decision framework, or which is very, I would say, snapshot modes. If you didn't create this design, definitely you will have a lot of overfitting, and you will be always coming to the best value because basically you didn't do a lot of uncertain training. Another thing for the detection, yes, detection as well have the same issue. If you have a data, firstly, you are very confident, it's very supervised learning, it's very labeled, it's very simple, very small data, definitely you can have 100%. Normally in our work, we reject any 100% or 99.99% as accuracy. You need to make sure that the data is, I would say, strong enough, very diversified, and as that's why we generate uncertain samples, adversarial samples, to make the data more augmented and more generalized, so that you will never found issue with either overfitting or underfitting.
Super. Well, I think with this, I'll conclude the webinar. Thank you so much, Dr. Alaa, for your time. You will receive a nice plaque from UND. And while you guys are here, we want to also to encourage you to come to our cybersecurity conference in October and submit papers. And we are the 6th year for IEEE CARS conference, and we need your continued support. And we also have National Security Agency is going to be a co-sponsor for this year as well. So I would appreciate more participation for our conference. And thank you.
Thank you so much. Yeah.